Okay, now we come to the example relating what we learned in the reflection transmission theory section to the wave that we've been studying. We've been applying this example, and then we've done it several times. We said there was an incoming wave, 0.52 sine of 6.95, x minus 2.6t plus 0.51. And then, of course, from the equation itself, we know that the wave number is 6.95 rads per meter. The velocity is 2.6 meters per second. And then the tension of the wave was given as 20 newtons, the tension of the rope that this wave is in. So from there, we calculated the velocity of the wave by applying b equals square root of t over mu. Well, we already knew the velocity was 2.6. And then if the tension is given as 20 newtons, we can calculate the mu, and then the mu came out to be 2.959 kilograms per meter. That was the mass density of the wave. Originally it wasn't given, but we calculated it using the fact that the tension is 20. Okay? And then the omega is 18.07, and then the frequency we found out is 2.8759. So let's say this wave is coming in, and then at x equals to 10 meters, it meets a boundary, right? And then at that boundary, there's another rope to the right of that rope, right? So this is the original wave, like this. And then let's say this is x equals 10 meters. And then at that boundary, there's another rope, like this. Right? It says the tension in that rope is 40 newtons. So you can hold two ropes that are connected. You can hold them in two different tensions. So the tension of this rope is 20 newtons. It's being held under 20 newton of tension. The tension on this rope is being held at 40 newtons. So it's a bigger tension. But the mass density of that rope is 4 kilogram per meter. So in this case, the rope's mass density is already given to you. So notice that its mass density is larger than here. This is 2.959 kilogram per meter. This is 4 kilogram per meter. So I drew it as a thicker rope with more mass per unit length, right? Then it says write the equations of the reflected and transmitted waves. So what is going to be the equation of the reflected wave bouncing back? What's going to be the equation of the transmitted wave that is going forward? Assume 70% of the energy of the incoming wave is reflected and 30% is transmitted. So that is a likely scenario that since this is lighter than that, upon reflection, most of it will reflect, some of the energy will transmit. So how do we solve something like this? Well, first what we can do is, let's keep this one intact. First what we can do is find the velocity of that wave. Find the velocity of the wave in this medium. Square root of the tension over the mu. So in this case, the tension is given as 40, and then the mu is given as 4. So velocity is going to be square root of 10. So that's going to come out to be equal to, right? So the velocity, the wave is going to be traveling faster in this rope versus the incoming rope. It's going to be traveling faster because the tension is more. But since the mass density was more, the two factors were competing against each other. The mass density was more, but the tension was even more. So it ended up that it's traveling faster here, okay? So what else, from then on, what can we do? Well, we could also find the wavelength of the wave in this medium. Velocity is equal to wavelength times frequency. Well, one thing that's going to happen when a wave goes from one medium to the other medium, this is also another interesting theory that is always true. The frequency of the wave will remain unchanged. Okay, that is something I didn't mention in the theory section for transmission reflection, but this is true for electromagnetic waves, and this is true also for waves in ropes. The frequency of the wave is fundamental to it. So what was the original frequency of this wave? We wrote it down here. The frequency was 2.8759 hertz. And remember, frequency is equal to 1 over period, and then omega is equal to 2 pi f. So the radial frequency, the angular frequency, which is measured in rads per second, and then the period, which is measured in seconds. So if the frequency is unchanged, that means the period of the wave is unchanged and the angular frequency is unchanged. So period, frequency, angular frequency is fundamental to the wave that is coming in, and it's independent of what medium it enters or reflects back from. Okay, frequency remains unchanged. Wavelength frequency is 2.8759, right? And then therefore the wavelength, since the velocity of the wave increases, the wavelength of the wave increases too. So we calculate this, we get 1.0995 meters. 1.0995 meters. The wavelength of the original wave, we had calculated it in the previous examples. It came out to be 0.904 meters. 0.904 meters. So the wavelength of the wave in here is going to be larger than the wavelength of the wave in the original, from the original wave. Okay. So now what do? We apply the energy equation, and then let's talk about the reflected wave, right? The energy of the incoming wave and the energy of the reflected wave. Well, it was told to us that 70% of the energy reflects back. So that means the energy of the reflected wave is 0.7 of the energy of the incoming wave, right? It's 70% of the incoming wave's energy. What's the equation for the energy of the incoming wave? Okay, the energy of the incoming wave is equal to 1/2 times mu times omega squared, a squared times lambda. So this we can say initial, initial, and initial. We know that the frequency is unchanged, right? And then the energy of the reflected wave, 1/2 mu final, omega squared, a final squared, lambda final. But notice this, the reflected wave is going back into the same string that it came from, right? It's just going back. The major thing that's happening is that the phase is shifting, but most of the other things are the same. The mass density of the final is the same as the mass density initial, because it's the same string. So this and this cancels, and then the 1/2 and the 1/2 cancels. Of course, the frequency of reflection or transmission is the same, so omega squared cancels. And then the wavelength is the same too, right? Because the velocity is the same, the velocity hasn't changed, the frequency hasn't changed, the wavelength hasn't changed. So this one cancels, this one cancels. So this one becomes pretty easy. The only thing is there's a 0.7 here because not all of the energy of the wave reflects back. Right? So then you have here a final squared is going to equal to 0.7 a initial squared. And then we can take the square root of that. A final is equal to square root of 0.7 a initial. Okay? So this is one thing that is also important when later on you study the concept of quantum mechanics, the phenomenon of quantum mechanics. You see that the energy of a wave is proportional to the amplitude squared of the wave function. Right? The amplitude squared is what packs all the information. So this is also true for regular waves in strings, electromagnetic waves, and also the wave function of a particle as given by Schrodinger's equation. So the amplitude squared carries the information about its energy. So then the final amplitude is going to equal to square root of 0.7, which is the portion of the energy that reflects back times the initial amplitude. So then what's that going to equal? The 0.7 a initial is equal to 0.52. This is the original amplitude. 0.52 a final. Okay? We calculate that and we get 0.435. 0.435. So what's the equation of the reflected wave then? We can write it here. The equation of the reflected wave is going to be 0.435 sine of 6.95. The wave number stays the same, the velocity stays the same for the reflected wave. But remember, it's going to the left, so you have to put a plus over here, right? So x plus 2.6t plus 0.51. Phase shift, yeah, this was a lighter medium, and the second wave was a heavier medium, right? So upon reflection, there was a pi radian shift. So we have to add pi to this. Okay? So two things happened in this case for the reflected wave. There was a pi radian shift, and the amplitude decreased because the energy of the wave decreased. So visually, it looks something like this. The wave came in like this, hit the boundary of the other string, And then the reflected wave should look a little bit smaller. So if this is the center of the wave, the middle, central axial line, so then the amplitude should be smaller. So if this is a 0.52 from here to here, this one is 0.435, so something like this, shorter, 0.435. Shorter in the sense of the vertical, the amplitude. The wavelength is the same, so it goes back like this. The wavelength is exactly the same. So it's going backwards now. It's going backwards. It's going backwards. So you can do this with a different color. This is the... So I should do this short, vertically shorter like this. Shorter. You see how this is taller like this? And then this is taller, but this one is shorter and shorter. And now, of course, if the two waves interact with each other, they will produce an interference pattern, right? If this one constantly comes in and then this one constantly bounces back, they produce a combined interference pattern. So this is the equation of the reflected wave. Okay, how about the equation of the transmitted wave? Okay, the transmitted wave is going to be a little bit harder to find the equation because more things change. So we have the energy of the transmitted wave is equal to 0.3 of the energy of the incoming wave. So we have the same equation now we write down, 1/2. So of course the omega squared is the same. The frequency does not change upon transmission. The half is the same, of course. Then we can write down all the other stuff. Mu final is going to be the mass density of the string of the second string, which was given to us already as 4. Right? So this one was 4. Lambda final, which we calculated, was equal to 1.0995 meters. So 1.0995 meters. A final, we don't know. Right? 0.3. The mu initial is equal to, we'll root this, and then the 0.52 squared can come out of the square root, and then multiply everything, and then we calculate that. And then when we do that, we're going to get 0.222 meters. So the amplitude of the transmitted wave is going to be smaller, quite a bit smaller. Why? Because the mass density is bigger, the wavelength is bigger, and only 30% of it is transmitted. Right? So all those factors. This one being bigger than this, the mass density being bigger, the wavelength being bigger. Why was the wavelength bigger? Because the velocity was bigger, right? Velocity was square root of tension over mu. So this one was bigger, and then this one was bigger than that, and then only 30% was transmitted. So all of those things caused the final amplitude to be smaller, okay? So A transmitted. So is there a phase shift upon transmission? No. So this is the only thing that happens. The amplitude goes down and the wavelength goes up. So let's draw that visually, and then let's write down the equation. Well, we can calculate what the K value is. K is equal to 2 pi over lambda, 2 pi over 1.095. Okay, and when we do that, we get 5.715, that's rads per meter. So we put that here, 5.715, then we get x minus, so the transmitted wave is still going to the right. So it's going to be just x minus the velocity. The velocity of the wave was, we wrote it earlier, it was 3.162 meters per second. Right, so it's Vt plus the phase angle, which is equal to 0.51. But that's it. We don't need to add pi, we don't need to subtract pi from that. So then that's it. We just close that. That's the equation of the transmitted wave. Okay? And now we could write down what it's going to look like. So what will that look like? Well, the amplitude is going to be much smaller, so let's do this in a different color. Okay? So let's do this in blue. So let's say this is going to be even, it's going to be even smaller than the reflected wave, right? So it's going to look like this. So this is the middle line here. It's going to look like this. And the wavelength is going to be bigger. So from the distance from here to here, the distance from here to here, but it's going to be bigger than that, right? So the wavelength is this one is half a wavelength. So even half the wavelength is going to be bigger, right? So it's going to be from here to here, it's probably here. So maybe here. So it's going to go like this. Like that. You see? The reflected wave is bigger than the transmitted, but they're both smaller than the original incoming wave. Right? So then it's just going to travel like that. So the wavelength gets bigger, 1.095 versus the wavelength of this. The velocity gets bigger, the wavelength gets bigger, the amplitude gets smaller. And then this wave will continue as long as that string exists, you know, until it reflects maybe from the other side. Then you can create standing waves also. So now if the problem tells us at a certain time and at a certain location, what's the value of the y transmitted and the y reflected? And if we want to find out their velocities, we can take the derivative with respect to t. It will tell us because these waves are going to be propagating up and down also. So we can find out Vy, Ay, we can take the derivative with respect to t, we can take the second derivative with respect to t, just like we did with the incoming wave, and I have an example of that, where we found out the vertical velocities of the waves, right? We took the derivatives and the derivative of this. You could do the same thing with the reflected and the transmitted waves, right? So let's just say, for example, the problem tells you at, let's say at, right? So remember the boundary was at x equals to 10, right? So then the wave is coming back at x equals to 5 meters and 10 seconds. What's the value of the y reflected? So remember, we're focusing on only the reflected wave. If the incoming wave is still coming, then we have to find out the y of the incoming wave, and then we would have to add those two, the y of the incoming wave to the y of the reflected wave. If we add those two, we'll get the combined y of the incoming wave and the reflected wave, the combination of the two waves. We call that the interference of the two waves, right? But if we only want to know the y of the reflected wave, we could put in the numbers, y reflected, radian mode when you calculate this, put 10 seconds, so this is going to be 26 plus 5, so this is going to be 31. 31 times this, plus this, plus this, put that in radian mode, take the sine of that, multiply it by 0.435. Okay, when you do that, you get negative 0.315 meters. Right? And if we wanted to take the derivative of that with respect to v sub y, we would take partial y, partial t. Right? We would take the derivative of that with respect to t, we would get another equation, and it would tell us the velocity in the vertical direction, and then we would take the second derivative of that, and it will tell us the acceleration in the vertical direction. Right? Then we could do the same thing for the transmitted wave. And then at 15 and 10 seconds, right? So we would want to know at x equals to 15, because the transmitted wave only exists after the boundary, which is at x equals to 10. So we can say, let's say at x equals to 15 meters and 10 seconds, what is the y of the transmitted wave? So then we would do 0.222 sine of 5.715, 15 minus 3.16210, plus 0.51. Right? So we will have to put 15 for x, and of course the k value is different. Then the velocity is different, right? 3.162, and then this is 10, and then the phase angle is still 0.51, right? Put that all in, make sure you are in radian mode. Y transmitted is going to be, then you should get negative 0.0496 meters. Okay, it's just coincidence that they both came out negative. It wasn't necessarily, it's not always going to be like that. Okay, so practice that, see if you get the same answers, and then watch the video again, and then hopefully with this it makes sense. So this topic of transmission reflection applies to, you will apply it to electromagnetic waves, you will apply it to quantum mechanics for the wave function of a particle. The wave function of a particle comes and hits a certain barrier, maybe reflects from that barrier, part of the energy transmits into that barrier. So when you study quantum mechanics, it also applies to that. Usually you will see drawings like this, like a wave function, and then you'll say there's a barrier here, and the wave function has a certain energy. Part of the energy of the wave, maybe it hits a certain barrier, part of the energy of the wave transmits. So find the wave function describing the transmitted wave. Okay, so all this concept that you're learning with strings, if you learn it well, then you can apply it to other topics. Okay, thank you very much.